Good evening everyone. In this video, I'll be discussing the electronic configurations of the elements with the atomic numbers 11 to 30. In previous video, I have discussed till 10, that means the atomic number of the elements till 10. So today we will start with the elements having the atomic number from 11. Okay. Now the atomic number which is 11 is that element is the sodium. Okay. Now we will be discussing here the orbital concept as I have told you in previous video. Okay, so it will start with 1s, 2 electrons will be there in 1s orbital, then another 2 electrons will be there in 2s orbital, 1s2, 2s2, then 6 electrons will be there in p orbital, 2p orbital, 2p6. Now we can count here how many are there, 2, 4, 10. Now another 1 electron that will be in 3s1. okay, so 1s2, 2s2, 2p6, 3s1. this is the electronic configuration of sodium. Now we can see the arrangement of the electrons present in different orbital. We can consider this is 1s orbital, this is 2s, and this is 2p. Now we know that 2p orbital has 3 suborbitals. Okay, so how the electrons will be there? And again, any kind of s orbital has only one suborbital. Okay, so this is the electronic configuration. Now we will fill the electrons. This 1s is the lower energetic orbital, so this will be filled first once. Then once it is totally filled by 2 electrons, then the electrons will go to the 2s orbital. Okay, so here is the 2 electrons, up spin, down spin. Here also 2 electrons, up spin, down spin. Now in 2p orbital, these 3 are the degenerate orbitals. Now how to fill these degenerate orbitals? First of all, each degenerate orbitals will filled singly, then the pairing will take place. Okay, now this is the 3s orbital. Clear? So this is the electronic configuration of sodium. Now come to the magnesium, which is 12. It will be 1s2, 2s2, 2p6, 3s2. Okay, similarly this will be same. This 3s orbital will have the 2 electrons. Okay, and this is the outermost orbital. This is the outermost orbital. Now come to the aluminium, which is 13. It will be 1s2, 2s2, 2p6, 3s2. Now the electron will go to the 3p orbital, 3p1. Okay, so we can write same. This is 3s, 2 electrons, and this is 3p, which has 3 suborbitals, and 1 electron is there, that means this will be here. Okay, now come to the next, sodium, magnesium, aluminium. It will be silicon. Silicon is 14. Okay, this will be 1s2, 2s2, 2p6, 3s2, 3p2. Okay, so here it will be 3s orbital that I have shown here, and in 3p orbital, as it has 3 suborbitals, this will fill singly. Okay, now come to the phosphorus. Phosphorus has atomic number 15, so it will start with 1s, 2s, 2p, 3s, 3p3. We'll fill here till 6 because p orbital has maximum of 6 electrons. Okay, can have. This 3p, 1, 2, 3. Okay, now here it is sulfur. 16, 1s2, 2s2, 2p6, 3s2, 3p4. Now these 3p orbital are singly filled up. Now pairing will take place from 2px, 3px. Okay, now come to the chlorine. Chlorine is 17. Up spin, down spin. Okay, these are the till chlorine. Okay, so you write this down, so I can rub it and I will start it. Okay, now let's start with the next one, that is argon. Argon, the atomic number of argon is 18, which is a noble gas. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, this is argon. Now the next one is the the potassium. The potassium having the atomic number 19. So what we will do, we will not write the total electronic configuration here. It will help us to write it shortly. We will take this electronic configuration of this argon. So we know that argon is 18. So we'll write it here. Now, as we know the series, that after 3p orbital, the electron will go to the 4s orbital, not the 3d. Why? Because the 4s orbital energy is less than the 3d orbital. So here the 4s orbital will be filled, then the 3d orbital. Okay, so it will be 4s1. Potassium 4s1, okay, not the 3d orbital will be 0. Now for calcium it will be 20, argon 18, 4s2. Okay, this one we have to remember that the energy of 3d orbital is greater than 4s orbital. So here the 4s orbital will be filled up first, then the 3d orbital. Okay, now come to the scandium. Okay, now I will tell you a trick to remember the from scandium to zinc. That is, you can apply this trick. Scandium is T V C M Phi Co Ni Ka Zin. Okay, STVCM Ficonicazin. That means scandium is SC, T for titanium, you can write Ti. Vanadium is Vri, chromium is Cr, manganese is Mn. Okay, now it is from 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now we will see some exceptions in copper and chromium. I will tell you that. So for scandium, this argon 18. Now we know that the 4s electron is filled already, 4s2. Now the electron will enter to the 3d orbital, 3d1. Okay, similarly in titanium, argon 3d2. Here the electron will slowly enter to the 3d orbital 1 by 1 till 10. Okay, vanadium, this will be 3d3, 4s2. Now for chromium, we can see here, we can feel like this 3d4, 4s2, but this electronic configuration is not exactly right. One rule is there which is called half filled full filled rule. If we can expand this orbital, you'll be able to know that this d orbital has 5 suborbitals. 1, 2, 3, 4, 5. D orbital has 5 suborbitals. So here we know that all these d orbitals, suborbitals are degenerate. So here the electrons will fill up singly. 1, 2, 3, 4. Now there is a 4s orbital. It has 2 electrons. Now the rule says, if the d orbital, we know that in d orbital maximum 10 electrons can be there. Now if a particular element in its electronic configuration, 10 electrons are there in the d orbital or 5 electrons are there, that electronic configuration is more stable. Okay, that means the element will try to be there in that electronic configuration. Now in chromium we can see the d orbital has 4 electrons. So it is neither half filled nor full filled. Half filled means it should have the 5 electrons, or full filled means it should have the 10 electrons. The chromium neither have 4 nor it has 5. Okay, so this is not the correct electronic configuration. This chromium will try to arrange its electronic configuration in such a way both these orbital will be stable. So what happens, one of the 4s electron jumps to the dz2 orbital of the 3d, and the correct electronic configuration of the outermost orbital becomes 3d5 4s1. So here you can see this d orbital is half filled. Okay, so this is not half filled. So what is the correct electronic configuration of chromium? It is 3d5 4s1, 3d5 4s1, not 3d4 4s2. Okay, now for manganese it will come as similar with that the 4s orbital will filled first, then the electron will come to the 3d orbital, 3d5. Okay, now for iron it would be similar, 3d6 4s2. For cobalt similar, 3d7 4s2. For nickel 3d8 4s2. For copper, now here is again the exception. We can write that this is 4s2 3d9, but it will be 3d10 4s1 by the half field full field concept. This 3d orbital will be fulfilled and it will be more stable electronic configuration for copper. Okay, now for zinc it is 3d10 4s2. So here you can see the for chromium and copper it is not going with the usual rule. There will be a half field full field concept we have to apply here. Okay, so I hope you have understood this concept. Okay, so in next video I'll be discussing the other electronic configuration. We'll be starting with the S block, D block and P block. That means from the periodic table I'll be trying to make you understand the electronic configuration. Okay.